Okay, so we'll start with the final from 2 years ago. Perform a depth first search on this graph. Right? Let me turn this on so I can see if it's on there. And we'll use lexicographic order to determine the next vertex to visit. So we'll start at A, and then if we have a choice of things to still go to, that means that we're going to go to the next one in lexicographic order. So we'd go with B, then C, then D, etc. Right? So we'll go ahead and start at A here. And if I start at A, and what else? Indicate the discovery order and the finish order of each vertex. So vertex, discover, and finish. Okay? So we'll, of course, start at A, and we've discovered it at 1. We color it gray because we've visited it, but it's not done processing yet. We haven't finished it yet because we still have more of the graph. We go deeper in the graph before backtracking and finishing things. We look at its neighborhood, and we see B and C, so which one do we go to next? B. And its discover time is 2. Right? And then it's colored gray. We're at B, and it has a rather large neighborhood here, but we don't consider A because it's gray and it's already visited. But we would consider E, C, I, and F. So where do we go next? C. Right? And its discover time is 3. Right? So if you want to go along here, you can also draw the tree edges. From C, and then now it's gray here. From C, well, we're connected to a gray edge and another gray vertex. So our only choice here is to go to E next with a discovery time of 4. Right? And there's a tree edge. At E, well, B, we've already discovered it. So our only other choice here is to go to F. And its discovery is 5. At F, we could go to B, but it's a gray. So our only choice here is G. And it's discovered at 6. At G, we look at its neighborhood here, and it's D and I. So D is next. And at that point, we've reached A. We went to from E to F. That's a tree edge. And then over here. At this point, it's a dead end, so we backtrack. So D is finished at 8. Right? And then we go to I, and it's discovered at 9. Okay? At which point we're done, and we would end up backtracking all the way. 10, 11, 12, 13, 14, 15, and 16. Right? At that point, everything would be colored black here because it's done. We've finished all of them. We've processed them all. Okay. All right. Same graph. Perform a breadth first search starting at A. Use lexicographic order to determine which vertex to visit next. Here I'll go ahead and draw a BFS tree. Right? Indicate the discovery and order and finish time of each vertex. So here's A. We visited its entire neighborhood, but in order, B, C next. So 1, 2, 3, and then it would be, again, it's indicate discovery order and finish order. They're going to be the same thing. If you wanted, if it asked for timestamps, they'd be slightly different. It'd be 1, 2, 3, and then we'd finish at 4. All right? But otherwise, you can, by drawing the tree here, you can come back and label them all 1, 2, 3, 4, 5, 6, and just go in that direction. All right, B's next, and we look at its neighborhood of E, C, but C's already been discovered. So E, I, and F. Is that the correct order? E, I, A, B, C, E, F, G, H, I. Okay, so F is next. I always have to sing the ABCs in my head or aloud. Right? And from B, we go to E. E, F, I. Right? And then we come back to C and process it, but everything else in its neighborhood has been processed already. E, A, and B. Oops, sorry. E, A, and B are already part of this tree up here. Okay. So nothing's hanging off of it. We next go to E, and that's right here. B's already been discovered. F has already been discovered, so it's done. E has already been discovered. B has already been discovered, but G has not. So we visit G next, but we don't go on yet. We go over to I next. and look at its neighborhood. G has already been discovered, B has already been discovered, so it's done. So the next one will be G. Off of G is hanging D, and so there's the BFS tree. And the order, of course, would be 1, 2, 3, 4, 5, 6, 7, 8. Did I miss one? I don't think I did. Nope, there are only 8. Okay. All right. Compute a minimum spanning tree for this graph. Indicate which algorithms you're using and the order in which the edges are considered and whether or not they're taken or not taken. So what do you want to do? Do you want to do Kruskal's or Prim's? Kruskal's? I heard Kruskal's considers them in order of least weight to greatest weight and builds a tree as long as it takes them as long as it does not induce a cycle. So let me go ahead and clean this up. Okay. So we'll go ahead and edge order. So which was the first one that we consider? Well, the least weighted edge here, so BC, with a weight of 2. And the result is that we take it. Because of course we're starting out here, so there we go. And we're doing Kruskal's. Okay. The next one that we consider would be one that's weighted 3, either this one, or this one. We'll go ahead and break ties arbitrarily, or we can break them according to lexicographic order here. BE for 3. The other one would be BF for 3. And the other one would be, where was the other? GF. Or FG. Let's go in order. There we go. So BE, would I take it? Yep, that wouldn't induce a cycle. So take. BF, would I take that? Yep. And FG, sure, I'd take that too. All right. So take, take, take. Okay. What's the next one that we consider? These 4s, this 4, this 4, and this 4. So A, C of 4. Would I take this one? A is not connected, so yeah, sure. All right. The next one I would consider is either EF or DG. So DG, lexicographic order, and then we would consider EF. So take. Now DG. Well, that would not induce a cycle, so take it. This is ending up not being very interesting, is it? Oh, now it's interesting. Actually, is it interesting anymore? Yes, it's still interesting because why? How many have I taken so far? 1, 2, 3, 4, 5, 6. How many do I need to take? Remember, there are 1, 2, 3, 4, 5, 6, 7, 8 vertices, so I need, in a minimum spanning tree, I need 7 edges, so I need 1 more. Is that 1 more going to be this one? Nope, it'll be a cycle, so no. Okay. What do I consider next? EC, do I take it? At a cost of 7? No, because it would induce a cycle here. Okay. Quickly running out, but the next one is the one that I do actually take, and it's going to be IG, or A, B, C, D, E, F, G, H, I, IG, a weight of 10, take, and then stop. Because you've taken 7 edges. Right? And you know that it's a connected graph. Of course, if it were a disconnected graph, then you wouldn't hit this number 7 ever. You would just have a forest with fewer edges. So what's the total weight of the minimum spanning tree? Well, it's going to be all of these, which is going to be 8 and 9, so 17, 18, 19, plus 10, so it's 29, right? Okay. That's Kruskal's algorithm. Of course, if you wanted to do prims, that would be perfectly fine as well. Simulate Dijkstra's single source path algorithm for the source being I. So throwing you for a loop here starting from I. Right? And it's important where you start because remember Dijkstra's is a single source shortest path algorithm. Okay? So we're going to start at I here. Right? And we're going to consider, let's see, we kept track of the predecessor vertex and the cost to get there. So by putting this in, there's no predecessor, it costs you 0, and there's no predecessor. And so we'll put that over here in the final. Right? And over here will be our heap. Right? And we'll be modifying this, but I'll go ahead and draw it while we go along. And I look at its neighborhood, right? I look at the neighborhood here. I can go to G at a cost of 10 with a predecessor of I. Right? I can go to B at a cost of 25 with a predecessor of I. The rest of them are all infinite, right? I can go to A, B, C, D, E, F, G, H, and then I is already taken care of at an infinite cost on all these. And no predecessor because I haven't seen them yet. Okay. Now on the next iteration, I choose the minimum here, which is going to be, of course, G going to 10 with a predecessor of I. And so now that's out of the heap. And I look at the neighborhood of G now, and I see that I can now get to D at a cost of, well, you can get to G at a cost of 10, so going from G to D would be a cost of 14. Is that better? Yep. So we update this to be 14. And the predecessor in this case is going to be G. Likewise, I can get to F at a cost of 10 plus 3, 13, with a predecessor of G. Right? So 13 and a predecessor of G. Okay? On the next iteration, I choose the minimum, and since that's this one, it's going to be F, 13 with a predecessor of G. And now that's out entirely. I look at its neighborhood, and I and G are already out, and F is already out. So let me go ahead and highlight in pen now all the edges that end up in Dijkstra's algorithm. So I look at the neighborhood of F here, and I can see B and E now. And I could get to F at a cost of 13. So to get to B from there is going to be a cost of 16. And is that better? Previously I could get there at a cost of 25. But if I go over here, and then go over there, it's only a cost of 16. So yeah, certainly I update that. So 16 with a predecessor vertex of F. I look at the rest of the neighborhood here, and I'm not taking that yet. I'm just updating the heap. E at a cost of 17 with the predecessor vertex of F. Right. On the next iteration, I take the minimum here, which is going to be D14G. And so now that's gone. And what I did there was I took this one. But if I look at the neighborhood, I'm not going to end up updating any of this stuff. Right? On the next iteration, I take the next minimum, which is going to be B16 with a predecessor vertex of F. So I ended up taking this one right here. I now look at B's neighborhood of things that are not already finalized, and that's going to be E, A, and C. Okay? I can get to B at a cost of 16, and now I can get to C at a cost of 18. Is that better? Yep. 18, and by the way, this one's out with a predecessor of B. I can get to A at a cost of 16 plus 12, 28. So that's better than infinite. Predecessor vertex of B. And I can get to E at a cost of an additional 3, so 19. Is that better? Nope, so I don't end up updating that. Okay? Next iteration, I take the next minimum, which is going to be E, cost of 17 from F. So this one right here is the one that I take. And then I look at the neighborhood here of C and B, but B has already been finalized. C, however, has not. I can get to E at a cost of 17 and go on to C at a cost of 7. So that's going to be 24. Is that better? Nope. So I end up not doing anything. This one's now out. C, 18, and B. That one is now out. I look at the neighborhood of C here. By the way, going from E from B, so this one is how I know that I got that one. Okay. So now I look at the C's neighborhood here. B is already done. E is already done. The only thing that's not done is A. Oh, that's why we're not getting this. There's no such thing as H here. There we go. I was worried, like, where is that going to come up here? No, it's not there. All right. So I can get to A from C at a cost of 18 to get to C, and then 4, so 22. That's definitely better. And I update my predecessor vertex here to C. And on the next iteration, I take it, 22 and C. So I go from C over to A. There we go. All right. That graph might have been designed for an interesting Dijkstra's and not an interesting, and it ended up not being as interesting for some of the others. Okay. Come on. Really? All right. That's the end of that graph. Design and analyze an algorithm that, given a weighted undirected graph G, computes the maximum spanning tree of G. All right. So instead of minimizing the overall cost, we want to maximize the overall cost of a minimum spanning tree. Maybe the edges are rewards that we get for traveling along there, but we can't, whatever reason, we can't travel too much or something, I don't know. You can't travel in a circle. Right? Ideas. Modify Kruskal's to, well, how did Kruskal's work? We considered the minimum, then the minimum, then the minimum, and we took it. If it didn't induce a cycle, we left it. If it did induce a cycle, what could we do instead? To consider edges in descending order instead. And that will work. Idea 2, take the reciprocal of all weights. So if you had a weight of W, simply just take a weight, your new weight is 1 over W. And now run a minimum spanning tree algorithm, and it gives you the maximum value, because all you had to do was take the reciprocal. Right? Larger denominator means smaller number. Okay? And then write out the details. I'll leave that as an exercise. Give an example of a probability distribution on 3 keys whose optimal binary search tree would have depth 2. So we want a tree that with 3 keys that looks something like this, or it could look something like this, or it could be skewed to the left or skewed to the left, then right. Right? Let's go ahead and consider this. Give me a distribution on keys such that this is optimal. what would I need to do to make this optimal? Right? Normally you want, in a binary search tree, you want balance, right? And if and under certain key distributions, that's not the case. Some key distributions, it's by balancing it, you put one of the keys lower than it should be when it's up here, right? So this would be key 1, key 2, key 3. In fact, if you consult the notes, I think the example I gave you would require a skewed tree to the right, right? So you can check that out. But basically all it is, I don't know, make sure that whatever key, one of the extremal key values, either K1 or K3, in this particular case, if we're going to skew it to the right, K1 has to be highly, highly weighted, 0.98, right? Now it's okay, it doesn't matter what the other two are, right? Go ahead and put them as equal distributions. It doesn't matter because either this one or this one would work. And that's a distribution that no matter what, you want to sacrifice balance here to ensure that this key that's searched for 98% of the time is at the root. And this definitely has depth too. Okay? Give an example of a probability distribution on 3 keys whose optimal binary search tree would not have the key with the maximum probability at the root. Should have looked at my answer key before I got here. No, it's we would just need to make sure that the weight on this, on the maximum, let's see, is only slightly greater. So what do we want? We want, let's see, maybe 0.4, 0.4, and 0.2. Would that do it? Now what's the average number of key comparisons? It's 0.2 plus 0.4 times 2 times 1, 0.4 times 2, 1, 2, 1, 2 over here. This will end up being 0.8, 0.8, so 1.8. Is that right? But if we have, I think this will work because here we do like balance. What if we put one of these as the root? What if we put 0.4 as the root? That would necessarily skew everything to the right. Remember, it's still a binary search tree. K1 is less than K2 is less than K3. So we have to preserve the binary search tree properties. So I would have, if I put this one as the root, then I would have to have all of these skewed to the right. Now, what's the average number of key comparisons here? Well, yeah, you save on that root. You pay slightly more for the second one, but now you're paying huge for that third one. And this is going to be 0.4, 0.8, and is like 2.0, right? Which is even worse, okay? Skewing it the other way, of course, would be worse, and you could put maybe you want to do 0.5045 here to break ties, 0.35 here, or something like that. But that's the basic idea, right? Over here, balance is better because you're willing to pay more for this one. Slightly more for this one, as long as you're not paying a lot more for this one down here. That's the idea. Give an example of a probability distribution on 3 keys whose optimal binary search tree would be balanced. Well, cut, paste, done. That would be balanced. Recall that the dynamic knapsack solution fills out a tableau of size NW. However, it is also known to be NP complete. Give a short explanation of why this does not imply P is equal to NP. The explanation is that NW is pseudo polytime, right? W is not bound by order n to the k. W could be order 2 to the n, in which case NW is going to be order n2 to the n, right? Exponential. In other words, it's not polynomial. It is pseudo-polynomial, fake polynomial. Okay? Below is a tableau generated by a knapsack with instance W is equal to 10. So that's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 8, 7, 6, 5, 4, 2, 1. And here are the items, A1, A2, A3, all the way up to A7. Right? Indicate which items make up the optimal knapsack. So in this one, all you have to do is simulate that backtracking algorithm that you're probably, hopefully, 90% completed with actually programming. You start at the bottom here, and then you look up. And there's a difference. So did we end up taking A7? Yep. A7 has a weight of 1. So where do I jump now? I just go 1 over, right, to this one, because it only had a weight of 1. Okay? So I look at the one above it, and there is a difference, meaning that I took A6. So A6, you took it. Right? Now A6 has a weight of 5. So when I go up here, I need to jump over 1, 2, 3, 4, 5. Because my capacity went down from 9 down to 4 by taking A6. So now I'm here. Did I take A5? Nope. Did I take A4? Nope. Did I take A3? Yep. So A3. A3 has a capacity of 3, so when I take it, I go all the way down to 1. At which point this is 0, telling you that you didn't take anything more. Right? Now it matches up here, so you could keep going up, and then go off the grid, but that's the end of the algorithm. That is your optimal solution right there. And hint, what is it? What's its value? 30, 11, 29. Check your work. What does that sum up to? 70. Right? You got that on your homework. Although, any questions? No? Okay, you're working on it. Suppose you have free access to the following algorithm, A, G, K, which takes a graph G and an integer K and outputs true if G contains a clique of size K and false otherwise. Design an algorithm to find the size of the maximal clique in the graph G. Well, if I've got free access to this thing, all I need to do is ask questions. What's the absolute maximum clique that you could have in a graph? If there are n vertices in the graph, they could all be the clique. It could be a complete graph, right? So start out at n. Are there any? Is there one of size n? Is there one of size n minus 1? Is there one of size n minus 2? Once you get an answer of yes, you're done, right? So for k running from n down to, well, the trivial clique is going to be a clique of size 1, right? An edge, a vertex is connected to itself at least, right? If A on G, K is yes, then output K. That's the maximum clique in that graph. Design an algorithm that takes a graph G as input and outputs a subset that represents the maximal clique. Okay. This is kind of what you're doing, similar to what something that you're doing right now. Right? The question I want to know is, okay, I think that for an exam, all we were thinking about was, once you've got K, right, you can output all subsets of size K, which is technically going to be order n to the K, right? And we didn't ask you to find an efficient algorithm here. So you could say for each subset C of V such that the size of C is equal to K. And then you verify all this stuff. For each pair X, Y in C, if X, Y is not connected, then it's not a click. Is click equals false? And so I need this flag variable here. Is click, we'll say that it's true, right? And if you are able to verify that it's a click, then output if is click, then output C. And that's it. That's all we were looking for in an exam. Now you can be a little bit smarter about it, and because this is going to be order n to the k, what k could be exponential. This could be exponential if k is like n divided by 2. Right? That's going to be maximized there. So what you could do is you could do something clever, for each vertex. Here's the clever one that is much better, right? For each vertex X, remove X from G, right? And then you ask your oracle, is there still a click of size K? Right? K is going to be the max click size, right? So if G, call this G prime, right? If A on G prime K is yes, then we know that X is not needed in a max click. Okay? So permanently remove it. Don't put it, else X is needed. So replace it back in G. Right? There. At the end, output G prime. Whatever, because all you have to do is, what is my click of size 5? And here are my 15 vertices. Right? Take out this vertex and ask your oracle, is there still a click of size 5? If yes, okay, well I didn't need that one. Right? Take out the next one. Is there still a click of size 5? Yes, okay, I don't need that one. Right? And eventually you whittle it down to the 5 that you need. If you ever do take this out and throw it away, and the oracle here says, no, there's no longer a click of size 5. Oops, I needed that one, put it back in. Right? And all you have to do is whittle it down to the ones that you actually need. Okay? Very similar to your homework. Hopefully I'm not repeating anything here. But if not, fine. I'll give high-level explanations. You still have to put it into your own words. It is a repeat. So I used to put stuff like this in finals. It never went well, so I put it in homeworks now so that you have much more time to think about it and time to ask questions and stuff like that. Suppose that P, so draw the landscape when you do stuff like this. P1 is in P. Right? This is P and this is NP, and say that this is NPC, NP complete. Before gaming became big, and we always say NP, now NPC means something in gaming, right? Non-playable character or non-player character? Okay, right? Well, it always meant NP complete since the 70s, right? Before all that stuff, right? So P1 is down here in P, and P2 is a click problem, so it's going to be NP complete. Suppose that we were to show that P2 actually reduces to P1. Does this mean that P is equal to NP or P is not equal to NP? And it means that P is equal to NP because everything reduces to the click problem, the clique problem reduces to something that's computable in P. Therefore, everything can be reduced to clique, reduced to this, and solved in P. Therefore, it's all collapses. Right? Suppose that they're not equal, and let P2 be in P. So here's P2. And let P1 be the Hamiltonian problem. Can we say that P2 reduces to P1 or not? Absolutely. That's the definition of NP completeness. Right? Hamiltonian path is an NP complete problem, NPC up here. And so everything, by definition, everything reduces to it. So yeah, absolutely. By definition of NP completeness. Say that P1 is in P, and P2 is NP complete. Can we conclude that P1 reduces to this? Yeah, it's the same question in disguise. This one just tests to see whether or not you remembered that Hamiltonian path is NP complete. Say that P1 reduces to P2. Can we conclude that P2 is a harder problem? Is that what this means? No. It is at least as hard. Right? Harder would be strictly less than kind of concept. And that's not what this is. It's less than or equal to, meaning that if P is equal to NP, well then everything becomes equal, right? With all polynomial time reductions. So that's not the interpretation of reductions. The interpretation is relative complexity. The other way we don't know yet. Let P1 be an NP and let P2 be an NP, so they're both somewhere in this landscape. Can we say that both of them reduce to each other? Why or not? Why not? And probably not, because what if, if both of them were in P, then sure, they reduce to each other, right, under polynomial time reductions. If they were both in NP complete, then yeah, by definition, they would reduce to each other. And if P1 is up here and P2 is up here, then certainly the reduction goes up that way. But does the reduction go down this way? Not unless P is equal to NP. Right? So no, because no, not unless P is equal to NP. Right. Let P1 be a problem. Is it true that it reduces to itself? Yeah. Why? Do you remember what iota is? It's the identity function. X maps to itself. You can always map a problem to itself. Input X, output X. Right? Here's def iota X, return X. There's some Python. Oh, no, there's some Python for you. Right. Okay. Yeah, go ahead.
If you have two problems in the same space, but they're different problems, do they also reduce them to each other?
Let's see. So, give me a scenario. They're both in P?
Yeah.
Under polynomial time reductions, yes. P1 reduces to P2, and P2 reduces to P1. Why? Because you can use and abuse the power of the reduction to simply solve the problem and do a trivial mapping of 0 and 1. 0 if it's not in the language, 1 if it is in the language. And now, that's why polynomial time reductions within P don't make much sense, because you can abuse the power of the reductions. Now that's why also under P1, under NP reductions, like if I gave you the power of NP, what could you do with your reduction? Well, you could solve any problem in here with the reduction itself and then do a trivial mapping of 0 to 1, or 0 and 1. So that's why we don't want our reductions to be too powerful. Now, if you really get into structural complexity, if you want to, winnow your focus down to just P here, and the complexity classes within that, you have to throw out these reductions because those are way too powerful now. And you have to start talking about log space reductions or truth table reductions, right? Or AC0 reductions, which are circuits of unbounded fan-in and constant depth. So what can you do with constant depth circuits? And that gets down into, here's L here. And then if you want to focus in on L, you can no longer use L reductions. You have to go to something more restrictive. So the further you go down in this hierarchy, then you have to use more and more restrictive reductions. Right. Good question, but that's a complexity theory question. And if you're interested in complexity theory, I forget what the number is, but it's not offered next semester. But so, wash, rinse, and repeat. You've got another graph. You can do DFS. You can do BFS, minimum spanning tree, Dijkstra's. I don't ask Floyd's for very good reason. If I gave you Floyd's on this, how big would your matrix be? 1, 2, 3, 4, 5, 6, 7, 8. 8 by 8 matrix, 64 times 8 operations. That's going to be times 8 iterations of that loop. That's why I'm not asking you to do that. Right. Okay. So do you want to see any one of these algorithms again on a different graph? Dijkstra's? Okay. Go with Dijkstra's here, starting at F. Right. So F, 0 weight, and of course, no predecessor there. So we look at its neighborhood, and we see A and G. A at a cost of 5 with a predecessor of F just going directly towards it. G with a cost of 8 with a predecessor of F. And the rest of these are all going to be infinite. So A, B, C, D, E, F is already done. G, H, yep. Infinite, 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 infinite. Nothing, 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 nothing. There. There's my heap. Okay, so I take the minimum out, A, 5, and F. So this is in my Dijkstra tree, if you want to call it that. It will end up being a tree, because if you had a cycle in a Dijkstra's solution, then why are you taking that cycle over and over again to just go somewhere? You just go there directly, right? So that comes out. And now we update things based on the neighborhood over here. A is connected to B at a cost of 5 plus 3. So we can get to B at a cost of 8. That's better than infinite. From our predecessor A. We can get to D at a cost of 5 plus 9. So 14. That's better than infinite. With the predecessor of A. Okay. So I took this one. Next one I take, well, I can break ties arbitrarily, or I'll go ahead and go with lexicographic next. So I'm taking this one right here. And I look at B's neighborhood here. I can now get to D at a cost of, to get to B cost me 8. So it's going to cost me another 7, 15 to get to D. Is that better? Nope. I can get to E at a cost of 8 plus 4, so 12. That's better than infinite. My predecessor is now B. And I can get to C at a cost of 8 plus 2, so 10. And that's better than infinite. And this is a predecessor of B as well. All right. Next iteration, I take the minimum, which is going to be G, 8, and F. So from F, go to G. That's part of my tree now. That's out of there. I look at its neighborhood, and I can get to G at a cost of 8. I can get to D at a cost of 8 plus 10, 18. That's not better. I can get to E at a cost of 11. That's better than that. So I update this to 11. And my predecessor is now G. I can get to H at a cost of 8 plus 11. So I update this infinite to 19 with a predecessor of G. Next iteration, I take the minimum here, so that's going to be C, a cost of 10 from B, that one right there. And that's out. Now I look at its neighborhood, but B is already taken care of. H, I can get there at a cost of 10 plus 12, so 22. That's not better. So I move on to the next iteration, take the minimum, E, 11, and G. So from G, I can go to E at a cost of 11. I look at its neighborhood. B is already taken care of. H is not, however. I can get there from with a cost of 11 plus 15. So that's 26, but that's not better than 19, so move on. Next one I take is going to be D, 14A. So from A, I go to D. And I look in this neighborhood here, but everything is already taken out. So my last iteration, I take H, 19 from G. There. Good? All right. Let G be a connected undirected graph. A cut edge is an edge such that when removed from G, separates G into two connected components. Design an algorithm that, given G, determines if it contains a cut edge or not. All right? So, for example, here's a graph, maybe like this, and it's connected to another part of it. This ends up being a cut edge, because if I took this edge out, there would be two connected components. This is not a cut edge right here, because if I took this out, it would still be connected like this. Right? So cut edges are nice, are very useful in, say, graph topology in networking to find the weak link. Right? That if this line were cut, New York and Chicago would not be able to communicate anymore or whatever, right? There has to be redundancy. If there's a cut edge, we need to make sure that we lay another line between Chicago and New York so that if this ends up going down, we can still communicate with each other. Right? That's the idea of a cut edge. Right? So how do we find out if one exists? Well, we can test, right? For each edge, E in E, remove E from G, producing a new graph G prime. Right? Then run DFS. One main iteration. Starting from an arbitrary vertex. If this were indeed if this were the cut edge, and I ran DFS over here, what color would all these vertices be at the end? It'd all be black because they'd be done, right? But I would still have unvisited white vertices over here, right? So if G prime still contains unvisited, and the way that we do test that is, white vertices, then E is a cut edge, and output that E is a cut edge. Otherwise, if you get through everything and none of these resulted in a cut edge, yes, then output no cut edge. Right? Absolutely. If you need to, you can write out a DFS, open book, open note, open computer if you really want to. But for this one, definitely not. If you needed to take DFS and then modify it, like maybe in your homework you want to use DFS to find the minimum path, right? Or if there's only one path, say, in a tree, you can write out DFS, add a counter up here, increment your counter somewhere, decrement your counter somewhere, use your counter somewhere. That's perfectly fine. Suppose that T is an OBST with n keys. What's the maximum depth of T? It's kind of a red herring kind of question here. N minus 1. Remember, depth has no bearing on it being optimal. It could be completely skewed, and that's optimal for that particular probability distribution. Right? And the maximum depth with n keys, of course, would be this kind of linked list kind of thing, ... And its depth is going to be n minus 1. Again, testing whether or not you understand the difference between a balanced binary search tree and an optimal binary search tree, which have completely different applications. Suppose we have n equals 7 keys and want to create an optimal binary search tree, but the probabilities are uniform. That is, each key has probability 1 over 7. What would the tree look like, and what would its depth be? If everything has equal probability, then does it matter if you put higher probabilities shallower in the tree or not? No. If everything's uniform, what's it going to look like? 1, 2, 3, 4, 5, 6, 7. There's a balanced binary search tree. Right? Otherwise, if you even skew it a little bit, then these things of equal probability will be deeper. These things of equal probability will be shallower. That doesn't buy you anything to make these shallower because you're making these deeper over here. So it'd be balanced. And what would its depth? What's the depth here? 2. Consider the following root table generated by an optimal binary search tree algorithm. Draw the corresponding tree. The keys are 21, 33, blah, 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 blah. Okay? So these are not indices here. These are references to the actual key. So where do I look to find the root of the entire tree? 1 through 8. So that's going to be 52. That's my root. All right? 1, 2, 3, 4, 5, 6, 7, and 8. So in the left subtree, I'm going to be looking through 1 through 4. So 1 through 4. The left child is going to be 21. Okay? 6 through 8. 6 through 8. The right child is going to be 93. All right? And there's no right child of 93. What did I say over here? 21. There's no left child of 21. What about 2 through 4? That's 35. All right. So there's that guy. And then, of course, now you don't even need to look up table anymore because it's going to be 33 and 38. Over here, there's no right child to 93. I'm looking through 6 through 7. So 6 through 7, that's 76. So 76 is going to be the left child of 93. And then that leaves 72 as the left child of 76. All right? Kind of messy, but you can write in pencil and then draft it out on a scratch sheet and then draw it nice and pretty over here. All right. I think they're mostly the same. We can look at them though. So this is a polynomial time reduction. We've got 3 problems here, P1, P2, and P3. So suppose that P1 reduces to P2 and that P2 is NP complete. So here's P2, and P1 reduces to it. Can we conclude that P1 is NP complete? Where might it be in this landscape here if P1 reduces up to this? By definition, it's going to have to because it's NP complete. Actually, it doesn't have to. It could be out here. Right? It could be over here. It could be over here. Right? It could be over here. This is definite yes. This is a definite yes. And this is a definite yes because P2 is NP complete. All 3 of those would reduce to it. But can we say that this one, it would not reduce to it, but can we say that P1 is NP complete? Well, here's one possibility. Can we say that P1 is NP complete then? No, right? Because it might be in P. P1 might be in P. In which case, if it did, right, then if it were NP complete, then it would collapse this this landscape here. Same thing, but P1 is NP complete, and P2 is an NP. Can we conclude that P2 is NP complete? So P1 is NP complete, or sorry, yeah, P1 is NP complete. Move this up here. And P2 is somewhere in here, so it's not out here. It could be in P, it could be over here, it could be up here. And we're saying that P1 reduces to it. Can we conclude that it's NP complete? Yeah, that's the definition, right? Everything reduces to P1, right? And P1 reduces to P2. Therefore, everything reduces to P2. So yes, it is NP complete. Right? Third landscape here, say that P1 is down here in P, and that P2 is NP complete. So P2 is up here. Can we conclude that P1 reduces to P2? Yeah, that's by definition. Fourth landscape. Say that P1 is NP complete and that P2 is in P. Right? And that P1 reduces to P2. Can we conclude that P is equal to NP? Oh, an NP complete problem reduces to something in P and therefore is solvable in P. Therefore, any NP complete problem is solvable in P, and thus P is equal to NP. Remember, going up is always trivial. You can always make things harder, right? It's more difficult to make things easier. Right? And again, you shouldn't interpret it like that. It's not harder, it's at least as hard, okay, technically.